Today we want to look at parameterized curves. The main reason we want to do this is that so we can describe a curve, a one-dimensional curve, in three-dimensional space. That's where we're headed with this. Let's talk about why we would want to describe a one-dimensional curve in three-dimensional space. So here's what we want to do. We want to describe a one-dimensional curve in R3. So we need a new mechanism to describe a one-dimensional curve in R3. If we have a function of three variables, if we have a function of two variables, if z is a function of x and y, I immediately moved you into R4, so we couldn't picture what was going on. If we have z as a function of x and y, we know that will produce a surface in R3. So recall some things we need to put together. Recall z equals f at xy is a surface in R3. So a function of two variables will produce a two-dimensional surface in R3. But we want to be able to describe one-dimensional curves in R3. So let's also recall what integration is about. We want to think of integration as adding up a bunch of values of the function, very generally. So integration is adding up a bunch of values of the function. Integration is adding up a bunch of values of a function. If we have an integral from a to b, of a function of one variable, what we're doing is we're evaluating the function at all the points between a and b and adding up those values, subject to some weight. We're just adding up values of this function. There's a lot going on here. We're assuming that the function is constant for some small change in x, and then we're using multiplication to calculate an area, length times width, but the length is always variable. So I is going from 1 to n, and then Riemann comes in and say, hey, use more rectangles. We're just adding up values of the function. Adding up values of the function. So that's what integration is about. We're evaluating the function a bunch of times, and then we're just finding the sum of those values, subject to some weights, and so on and so on. When we have so in the function of a single variable, the only subset of R1, when we have a function of one variable, the only collection of points that we're going to plug into the function is an interval from a to b. But when we have a function of two variables, we need a collection of points x, y. So we're talking about integrating over a region. And when we have a function of three variables, we're adding up a bunch of values from R3. But what we're doing is we're adding up a bunch of values from the interval from a to b in R1. We're integrating over an interval in R. That's the only collection of points that we can really have in R. Intervals. If we have more than one interval, separate intervals, then we have to do a bunch of separate integrals. So in all cases, we're just considering the function over a bunch of inputs. So the function f of x has inputs that come from an interval. In R2, when we integrate over a region, we're integrating over a region in R2. This is telling us what values of x and y we're plugging into the function, and then we're gonna that we add up. So we integrate over a region. That's the region that we're plugging into the function. That's the collection of points that we're plugging into the function. The integral, when we integrate over an interval in R, that interval is the collection of points that we plug into the function. Yikes. That interval is the collection of points in R that we plug into the function. This region is in R2. That's what we plug into the function f of x, y. And then we just continue this theme with more dimensions. So when we integrate over a solid of a function of 3 variables, this w is a solid in R3 that we plug into f of x, y. So w is a solid in R3 that we plug into f of x, y, z. It's just a collection of points in R3 that we plug into the function so that we can add things up. The region in R2 is a collection of points in R2 we plug into the function. The solid in R3, W, is just a collection of points in R3. All right. So now that we're plugging in collections of points in R3, when we integrate a triple integral over the solid W, we're taking all the points in the solid W and plugging them into the function. Because that's what we do when we integrate. We just take a collection of points, plug them into the function, and then add up the values. Multiply by some weight, dA, dV, dx, and then add up those values. We're just plugging in all those values into the function. But when we have a collection of points in R3, here we're taking a 3-dimensional solid of points and plugging them into the function. But that's not the only collection of points we can have in R3. Here's a 3-dimensional collection of points in R3 that we're plugging them all into the function. What if we take a smaller dimensional subset of points in R3? So specifically, this solid is a 3-dimensional collection of points in R3. So now what we want to do, what if we want to integrate a function of 3 variables, but only over a 2-dimensional collection of points in R3 or a 1-dimensional collection of points in R3? So instead of integrating over an entire sphere, all the points on the interior, what if we just wanted to integrate over a surface in R3, the surface of that sphere? Or what if we wanted to integrate a function of 3 variables over a one-dimensional curve in R3? So now we need some new mechanism for describing a one-dimensional curve in R3. Then we'll also have to consider what will be useful when we add up these values. What values of the function will be useful to add up? Any questions? What we want to remember moving forward is that when we're integrating a function, we want to think of it as just adding up a bunch of values of the function. Adding up values of the function, evaluating the function at all the points between A and B, and then translating that into something that will mean something. Because when I say all the real numbers between A and B, add up all those values, that's a very fishy statement. If you're like, oh, Leach, that sounds like a very fishy statement, then you are correct. That's kind of the integration version of me saying 1 divided by 0 is infinity. It's not really, but it kind of is. So this is the thinking that we want running by it. This is where we can start building an intuition about what integration represents. We're integrating over a region in R2. We're just plugging in all these values from this region into the function of 2 variables. When we integrate a function of 2 variables, I need a bunch of values x, y, a bunch of points from a region that I can plug into the function. When I want to integrate a function of 3 variables, I need a bunch of points x, y, and z to evaluate the function, and then just add up all those values. What we want to do now is, so far, it's always been all the points in a solid in R3, but there are different structures in R3. There's also a 2-dimensional surface can be in R3. We might want to add up the values there. Or a 1-dimensional curve in R3. Maybe there's just like the path of a fly as it flies around the room. And we want to add up the values of that path. But the solid in R3 is just a collection of points, x, y, z. A surface in R3 is just a collection of points, x, y, z. A curve in R3 is still just a collection of points in R3. Any questions? All right. All right, let's pause the video here and talk about parameterizing curves. This is where we're parameterizing curves, by the way. I probably should have said that. I just did. Saved it. All right, let's pause the video here and talk about parameterizing curves.